All right. So, when it comes to philosophy, you and I both, we really like to get to the core of things, cut through the noise, the distractions, and really grapple with the thinkers whose ideas have shaped how we understand the world. And I think that's why we're both drawn to this episode's topic. These figures who've, well, they've kind of laid the groundwork for so much of what we discuss.
Absolutely. And today we're diving into the work of someone who, well, he might not have always worn the philosopher hat proudly, but his influence on the field is undeniable. Alfred Tarski,
Yeah, Tarski, I mean, he described himself as a mathematician, a logician, and yeah, maybe a philosopher of a sort.
perhaps the philosopher of the sort.
Right. But, regardless of how he saw himself, his work, especially his rigorous, almost mathematical approach to these really fundamental concepts, has had a huge impact on philosophy. It's kind of working behind the scenes in so many contemporary debates.
It's like he provided the tools, the conceptual framework for tackling these really thorny philosophical problems. Yeah.
Exactly. And while he might have been hesitant to fully embrace the philosopher label, his work grapples with some of the most enduring questions in the field. Truth, logical consequence, the very nature of logical constants. These are all things that we as philosophers wrestle with constantly.
Right. And our aim today is to kind of distill the essence of Tarski's thinking on these matters
Yeah.
and present it in a way that's, well, as if we were having a conversation with another philosopher, someone who appreciates that
Wow.
kind of clarity and, well, the weight of these really fundamental concepts.
Yeah, exactly. We're talking to you, the listener, as a fellow philosopher, someone who's joined us on this journey of philosophical inquiry. And for this particular deep dive, we'll be drawing from the Stanford Encyclopedia of Philosophy entry on Alfred Tarski. It's a really comprehensive resource, really meticulously researched. So with that as our guide, where do we even begin with a figure like Tarski? Where do we start?
Well, I think a natural starting point, especially for philosophers, is his work on truth. Truth, it's such a basic concept. It seems so straightforward, so intuitive. But the moment you try to pin it down, to define it rigorously, well, it can become incredibly slippery. So what was it about truth that drew in someone like Tarski, a mathematician by training, to tackle such a seemingly philosophical problem?
Yeah, it's kind of strange, isn't it? You'd think a mathematician would be more interested in numbers and equations and such. Why truth?
Well, for Tarski, truth wasn't just an abstract philosophical puzzle. It was a problem that arose from within mathematics itself, from the foundations of logic. See, he saw that there weren't any precise, rigorous definitions for semantic notions like truth within the formal systems that mathematicians were developing. And he was also really concerned with avoiding those paradoxes, the liar paradox and others, those things that had just plagued attempts to define truth for centuries. It's like, how can you build a solid logical system if the very idea of a true statement within that system is somehow shaky?
Right. So he wasn't approaching it from some kind of purely detached, armchair philosopher perspective. He was trying to solve a real problem that was arising in the actual practice of logic and mathematics.
Exactly, and that really shapes his approach.
So how did he go about doing that? How did he bring this mathematical precision, this rigor to the concept of truth?
Okay, so his central strategy, I guess you could say, was to define what he called a truth predicate. Now, stay with me here, but he wanted to define this truth predicate for a specific language, what he called the object language. But he did it by constructing a corresponding predicate in a separate, more expressive language. This was the meta language.
Okay, so it's like we're talking about truth in one language but defining it in another language.
Exactly. And this truth predicate in the meta language, it applies to sentences in the object language. And the idea is it's supposed to pick out, to be coextensive with, those sentences that we intuitively recognize as true. Like we know they're true, but we want to formally capture that. And importantly, this definition had to be built from mathematically sound vocabulary. You can't use any sneaky circular reasoning.
So it's almost like creating a mirror image of truth, but in a different linguistic space, and making sure that this mirror accurately reflects what we understand to be true in the original language.
A perfect analogy. And to make sure that this mirror image was accurate, that this definition of truth was actually adequate, Tarski formulated what he called convention T. This is kind of the litmus test, the fundamental criterion for a formally correct definition of truth.
And what does this convention T entail? Like, what are the rules of the game here?
So it has two main parts. The first part says that for every sentence, let's call it P in our object language, the meta language has to be able to prove what we call a biconditional. P is true if and only if P, and here P is acting as a name for the sentence itself.
So it's like if we're talking about the sentence, the sky is blue, our definition of truth should guarantee that the statement, the sky is blue, is true, holds if and only if the sky actually is blue.
Precisely. It ties the formal, the symbolic representation of truth to what we intuitively understand as truth in the real world.
Okay, so that's part one. What's the second part of this convention, T?
Right. The second part is more about the scope of the truth predicate. It says that for any x, if x is true, then x is a sentence of the object language. So basically, it's saying that our definition of truth is specifically talking about sentences in our object language. Can't accidentally apply to things that aren't even sentences that are outside the system we're analyzing.
I see. So convention T acts as a kind of guardrail. It makes sure that our definition of truth is both anchored to our intuitive understanding of truth and that it's only applied where it's supposed to be applied.
Exactly. And Tarski himself argued that if you have a sentence P and it satisfies your definition of truth, so tree holds, then the first part of convention T, this biconditional, directly implies that P itself must be the case. So his formal definition aligns with that basic intuition we have about truth, that it reflects reality.
It's elegant, isn't it? He starts with this seemingly abstract mathematical approach, but he's really grounding it in a very intuitive, almost commonsensical understanding of what it means for something to be true. Now, you mentioned that he used this language of the calculus of classes, LCC, as an example. How did he actually go about constructing a truth predicate for that particular language?
Okay, so this is where it gets a bit more technical, but the idea is he defines truth for this LCC in terms of something called satisfaction. It's the satisfaction of a formula by an infinite sequence of assignments. Now, in the case of LCC, those assignments map variables to subclasses of individuals. But the idea is he provides a definition for what it means for a sequence to satisfy a formula. And he does this recursively. It's kind of like building blocks.
Recursively. Can you maybe break that down a bit for those of us who, might not be fluent in recursion theory?
Sure. So imagine you have a simple formula in LCC, like X is a subclass of Y. Now, an infinite sequence of subclasses satisfies this formula if and only if the actual subclass assigned to X by that sequence is actually a subclass of the subclass assigned to Y. So it's basically checking if the relationship holds under the given assignment.
So the formula is satisfied if the assignments make it true, in a sense.
Exactly. But now, imagine a more complex formula, like not X is a subclass of Y. Here, a sequence satisfies this more complex formula if and only if it does not satisfy X as a subclass of Y. It's building up from that simpler case.
Okay, so the truth, or satisfaction, I guess, of a more complex statement depends on the truth or satisfaction of its parts.
Precisely. And it goes on like that. For a disjunction, like X is a subclass of Y or Z is a subclass of W, a sequence satisfies this if it satisfies at least one of the parts. Either X is a subclass of Y or Z is a subclass of W. And for universal quantifiers, like for all x, fx, it's satisfied by a sequence if every possible sequence that differs from the original sequence only in what it assigns to x, if all those sequences satisfy the formula fx. So it's about checking all possible variations of the assignments for x.
Okay, so yeah, I'm starting to see this kind of recursive building blocks structure. You define satisfaction for simple cases, and then you use those definitions to build up definitions for more and more complex cases. And ultimately, this leads to a definition of truth for entire sentences in LCC.
Right, so for LCC, his definition of truth is that a sentence, and remember, a sentence in LCC is a formula without any free variables. It's true if and only if every infinite sequence of subclasses satisfies it. And since there are no free variables, the sentence's satisfaction doesn't depend on any particular assignment made by the sequence. So if one sequence satisfies it, all of them do.
So it's like if the truth of a sentence doesn't depend on how you assign the variables, if it holds true regardless of those assignments, then that sentence must be, well, true in a very fundamental sense. Now, one of Tarski's big motivations, as we mentioned earlier, was to avoid these semantic paradoxes, like the liar paradox. How does this whole meta-language approach help him sidestep that?
That's one of the really clever parts. Because the truth predicate, TR, always lives in the meta language, right? It's one level up. It's more expressive than the object language, the language whose sentences TRR actually applies to. So you can't even formulate a sentence within the object language that says of itself that it's not true. That kind of self-referential sentence, the liar paradox, you can't build that in the object language because the truth predicate isn't there. It's in the meta language.
So it's like a linguistic safety feature.
Hmm.
He's created a hierarchy of languages where you can only talk about the truth of a sentence at a higher level. That seems to kind of dismantle the very mechanism that creates the liar paradox. And speaking of hierarchies, the source also talked about this distinction between finite order and infinite order languages, LCC and LGTC, respectively. What's the significance of that for, someone trying to grasp Tarski's work?
Okay, so this gets to the heart of how the expressive power of a language affects your ability to even define semantic notions. So LCC, this language of the calculus of classes, it's a finite order language. It's order 2, to be precise. Its variables range over individuals and classes of individuals, but that's it. Now, infinite order languages, like Tarski's language is the general theory of classes, LGTC, they have variables that can range over individuals, classes of individuals, classes of individuals, and so on infinitely.
So LGTC is a much more powerful language, right? You can express a lot more within it.
Way more expressive, yeah, and that causes some issues. When Tarski was first working on this stuff back in 1933, he thought his method for defining truth couldn't be applied to this LGTC, at least not within what was called finite type theory, which was the main tool for building his meta-languages at the time. The problem was that for LGTC, this satisfaction relation, it involves quantifying over this whole infinite hierarchy of types. You've got to deal with individuals, classes, classes of classes, and so on, and it's not clear how to do that in a meta-language that's limited to a finite number of types. It's like trying to fit an ocean into a teacup.
So the very richness, the expressive power of LGTC seem to pose a challenge to defining its truth using a similarly structured but ultimately limited metalanguage. It's kind of mismatch, right? And this is what led him to his famous theorem on the indefinability of truth.
Exactly. What the theorem says is, if you have a language as expressive as LGTC plus EA, which is basically LGTC with some extra tools to talk about its own syntax, you can't construct a truth predicate within that language that satisfies convention T for the sentences of LGTC. At least, not if you want your meta-theory to be consistent. It's a real limitation.
Wow. That sounds like a pretty significant result. I mean,
Yeah.
it suggests that there's a kind of inherent boundary to our ability to fully capture the concept of truth for really expressive languages, at least using the resources of those languages themselves.
Right, you can't pull yourself up by your own bootstraps, so to speak. And the proof, it's quite clever. It uses a version of Gödel's diagonalization technique, which is this method that's really central to a lot of modern logic.
Diagonalization, that sounds familiar, but refresh my memory. How does that work?
Well, I won't go into all the details, but the basic idea is that in these really expressive languages, the languages that can talk about their own syntax, you can construct these fixed point sentences. They basically say of themselves that they have or lack some property. Like, think about this sentence. This sentence is false.
Ah, so it's like that classic liar paradox.
Yep, that's the idea.
But
But in this case, it's not just a paradox. It's a tool for proving the theorem. Because if you then assume that you do have a truth predicate in your language and it satisfies convention T, you can use this fixed point construction to derive a contradiction and boom, your theory is inconsistent.
So, in a sense, he showed that the liar paradox, while seemingly a kind of linguistic trick, actually points to a deep inherent limitation in our ability to define truth for these really powerful languages.
Exactly. But it's important to note that later on, Tarski himself clarified that you can define a truth predicate for even something as expressive as LGTC if you use even more powerful meta-theories, things based on transfinite types or full set theory.
So there's always a bigger fish, in a sense.
Right, but his point still stands. To capture truth for a language, you need a meta-language that's at least as expressive, if not more so.
That's really fascinating. It highlights both the power and the limitations of formal systems. So we've talked about truth, but what about logical consequence? It's another cornerstone of philosophical logic, and Tarsi had a lot to say about that as well, right?
Yeah, so Tarski's work on logical consequence, it's primarily laid out in his 1936 papers. He really dives into how we should understand this fundamental concept. And he starts by examining the view that was kind of dominant at the time, what was called the syntactical view of logical consequence.
Syntactical.
Yeah.
So focusing on the structure of the argument, the arrangement of symbols and whatnot.
Exactly. This view, which really gained momentum with the rise of formal deductive systems, it basically says that a sentence logically follows from a set of premises if and only if you can derive it from those premises using these purely formal rules of inference. like modus ponens or substitution, just these mechanical rules for manipulating symbols. You're not worrying about what the sentences mean, just how they're put together.
So it's a very kind of formal, almost mechanical way of thinking about logical consequence, like a recipe for valid arguments.
Exactly. And at the time, people felt pretty good about this view. I mean, it seemed to work well for mathematics, which was being formalized using these kinds of syntactic methods.
But Tarski wasn't entirely convinced, right?
No, he wasn't.
Yeah.
He saw some problems with this purely syntactical approach. One issue was with what are called incomplete theories, like this LGTC we talked about earlier.
Incomplete theory. Okay, so remind me again, what does that mean? For those of us who haven't memorized every technical term.
Sure, so an incomplete theory, it's a theory where there might be a universal sentence, like for all x, px, that intuitively seems to follow from all of its particular instances, like p0, p1, p2, and so on. But you can't actually derive that universal sentence from those instances using any finite number of syntactic rules within that theory.
So it's like you have all these individual cases and they all point in the same direction, but you can't make that final leap to the general statement using just the rules of the system. You need an infinite number of steps, and that's not allowed in a finite deductive system.
Exactly, and to address this, some logicians proposed adding something called the Pooh rule to the mix. It basically lets you infer a universal statement from an infinite number of particular instances. But Tarski was like, hold on, that rule is not finitary. It doesn't play by the same rules as our other inference rules. It's like bringing in a totally different kind of tool. And on top of that, there are Gödel's incompleteness theorems, which show that even if you add more finitary rules or axioms to your system, some theories, especially really rich ones, are just going to remain incomplete and Pooh incomplete too.
So you're saying that even with these new rules, there are going to be cases where a sentence seems to logically follow, but you can't actually prove it within the system.
Right, and that's what convinced Tarski that the syntactical view just wasn't cutting it. It just wasn't capturing the full picture of logical consequence. We need a different approach, something more robust.
And that new approach, the one he championed, was a semantic approach, right? One based on meaning and interpretation.
Hmm.
And it seems that his work on truth really laid the foundation for that.
Exactly. Instead of focusing on derivability using formal rules, he shifted the focus to truth preservation across all possible interpretations. So to illustrate this approach, he often used simpler formal languages as examples. One that he used a lot was a language of elementary arithmetic, which he called LRR. It's got symbols for things like natural numbers, a predicate for being a natural number, and a predicate for less than. And the key thing here is that in the intended interpretation, these predicates actually apply to the things they're supposed to. N only applies to natural numbers. M only applies to pairs of numbers where one is less than the other.
Okay, so it's a language that's designed to talk about numbers and their properties in a very specific way. And how does he use this to build up his definition of logical consequence? I know you mentioned something called condition F earlier.
Right, so condition F is kind of a stepping stone. What it says is, if a sentence, let's call it X, is a logical consequence of a set of sentences, K, then any uniform replacement of the non-logical constants in X and K, if it makes all the sentences in the new set K true, it must also make the new sentence X true. Basically, if you swap out the specific terms in the argument, but keep the logical structure the same, and the premises are still true, then the conclusion must still be true.
So it's like saying if an argument is truly valid, its validity shouldn't depend on the specific things you're talking about. It's about the underlying logical relationships.
Exactly. But Tarski argued that while condition F is a necessary condition for logical consequence, it's not sufficient. A language might just not have enough expressive power, enough different non-logical terms, to show that an argument is invalid through this kind of replacement method. You might think an argument is valid because every replacement you try that makes the premises true also makes the conclusion true. But in a richer language, with more ways to interpret those terms, the argument might actually fall apart.
So condition F is like a good first test, but it's not foolproof. It's possible for an argument to pass that test, but still not be logically valid in a more robust sense.
Right. And that's what leads Tarski to his main definition of logical consequence. He says a sentence X is a logical consequence of a set of sentences K if and only if every interpretation that makes all the sentences in K true also makes X true. So it's not just about some interpretations, it's about all possible interpretations.
So the truth of the conclusion has to be guaranteed in every possible way that the premises could be true.
Exactly. And that's where the notion of an interpretation comes in. For LEA, an interpretation is just a way of systematically assigning things from your domain to the non-logical constants in the language. Like you'd assign a set of things to the predicate n to represent the natural numbers, and you'd assign a specific thing to the constant 0 to represent the number 0, and so on.
Okay, so an interpretation is like creating a specific model, a world, where the sentences of your language have a definite meaning and can be evaluated for truth. And logical consequence holds if the conclusion is true in every such world where the premises are true.
Exactly. And to make this more precise, Tarski introduces this concept of a sentential function. It's basically what you get when you take a sentence and replace all the non-logical constants with variables. So instead of 0 as a natural number, you'd have x as a natural number. And these sentential functions, they're neither true nor false on their own, but they can be satisfied by an interpretation.
Okay, so we've got sentences, which can be true or false, and we've got these sentential functions, which can be satisfied or not satisfied. How does that all fit together?
Well, an interpretation satisfies a sentential function if, when you plug in the things that the interpretation assigns to the variables, you get back a sentence that's true in that interpretation. So for x is a natural number, if your interpretation assigns the number 0 to x, then it will satisfy that sentential function because 0 as a natural number is true. And then a model of a sentence is just an interpretation that satisfies its sentential function. And a model of a set of sentences is an interpretation that satisfies all the sentential functions of all the sentences in the set.
So a model is basically a world where all the sentences are true. And Tarski's definition of logical consequence, then, is just saying that the conclusion has to be true in every model where the premises are true.
Precisely. If every model of the premises is also a model of the conclusion, then the conclusion is the logical consequence of the premises. And he also gave a definition for what it means for a sentence to be logically true, which is basically that it's true in every possible interpretation.
So he's really taken this concept of truth and used it to ground our understanding of logical consequence in a very elegant way. And you mentioned that condition, F, that replacement test, that actually follows from his definition.
Yes, it does. If x is a logical consequence of k, in Tarski's sense, then it has to be the case that any replacement of non-logical constants that makes all the sentences in k true will also make x true. It's a consequence of the fact that the conclusion has to be true in every model where the premises are true.
So it's like his definition captures this intuitive idea of logical consequence being about truth preservation, and that's why condition F falls out naturally. Now, the last part of Tarski's work that we wanted to talk about was his thinking on logical constants themselves. What did he have to say about what makes a term logical as opposed to, say, mathematical or something else?
Well, Tarski himself recognized that even though his definition of logical consequence was a big step forward, it still relied on this distinction between logical and non-logical terms. You have to be able to tell which terms you can replace and which ones you can't when you're testing for logical consequence. And he knew that this distinction wasn't arbitrary. If you start treating things like if dot then or for all as non-logical, then the whole idea of logical consequence just falls apart. It becomes meaningless.
Right, because if you can just reinterpret those terms willy-nilly, then any argument can be made to look valid or invalid.
Exactly. But Tarski also acknowledged that it's not always clear what the criteria should be for deciding which terms are logical and which aren't. It's a tricky issue. He even suggested that the distinction might be relative to the specific context you're working in. Like in some systems, the membership, the symbol areas that we use in set theory, that might be treated as a logical constant. But in other systems, it's considered non-logical. It just depends on what you're doing.
So the line between logic and non-logic isn't always clear-cut. It can depend on your perspective, your goals, and the specific framework you're using. But Tarski did make an attempt to give a more general characterization of logical notions, didn't he?
He did. In his 1966 lecture, What Are Logical Notions? He proposed that a notion is logical if and only if it's invariant under all one-to-one transformations of the universe. And by notions, he meant things like individuals, classes, relations, basically anything that can be a part of a logical system.
Okay, invariant under one-to-one transformations of the universe. That sounds pretty abstract. What does that even mean?
Well, a one-to-one transformation is basically just a way of rearranging the things in your universe while still keeping everything distinct. Like if you have a bag of marbles, you can swap the positions of any two marbles, and you still have the same marbles, just arranged differently. And what Tarski is saying is that a notion is logical if its meaning and its application don't change when you do this kind of rearrangement.
So it's like saying that logical notions are about the fundamental structure of things rather than the specific identities of the things themselves.
Right, like take the universal quantifier, for all. It doesn't matter how you rearrange the things in your universe. For all still means for all. It applies to everything, regardless of its position or its name.
That makes sense. So, how does this apply to those terms that we traditionally think of as logical constants, like and, or, not, and the quantifiers?
Well, according to Tarski's idea, you can actually construct those things as invariant objects within a type hierarchy. It's a bit technical, but the idea is that truth values can be represented as sets, and the truth functional connectives can be defined as operations on those sets that don't change when you permute the elements. And the quantifiers, they can be seen as properties of sets of objects, and those properties are also invariant under permutations. So all those things we think of as logical, they fit into this picture of invariance.
So, it's like he's found this really deep unifying principle for understanding what makes something logical. It's not just arbitrary, there's this underlying structural property that they all share.
Right. And this idea of invariance, it got further developed in his work with Stephen Gavant, where they define a logical constant as a symbol that always denotes a logical object, something that's invariant under permutations. And this definition, they thought, could apply to a much wider range of formal languages.
And how does this all connect back to that Tarski-Lindenbaum theorem we talked about earlier?
So that theorem showed that in simple type theory, all the things that you can define in the language are invariant under permutations. So that means all the constants of type theory, including all those higher order quantifiers, they would count as logical constants according to Tarski and Javant's definition. It's like type theory is built on this foundation of logicality, in a sense.
That's really interesting. But what about those mathematical concepts that aren't usually considered logical, like membership in set theory? Would those also be considered logical constants under this permutation invariance criterion?
Generally, no. The thing about set theory is that it has this primitive notion of membership, represented by the symbol S, and this notion isn't invariant under permutations. Whether one set is a member of another set, that's a specific relationship between those two sets, and if you rearrange the universe, that relationship might change. It's not a purely structural property. So set membership isn't a logical notion in Tarski's sense, even though it's fundamental to set theory.
So even though set theory is a very powerful and foundational theory, it still relies on concepts that aren't purely logical in this very abstract structural sense. It has to engage with specific kinds of relationships that go beyond pure logic.
Exactly. And that kind of brings us back to Tarski's earlier point about the logical-non-logical distinction being somewhat relative to the context you're working in. In some context, it might be useful to treat membership as a logical notion, while in others, it might be better to think of it as non-logical. It all depends on your goals.
It's a very nuanced view, and it really highlights the complexity of these foundational issues. So, to sum up, Tarski's work on logical constants gives us this really powerful, though maybe still somewhat debated framework for understanding what makes certain terms so special, so essential to the way we reason. It's not just that they're commonly used or intuitively appealing, there's this deep structural property of invariance that sets them apart.
Right. It's like he's given us a glimpse into the inner workings of logic itself, the machinery that makes it all tick.
Well, this has been an amazing deep dive into Tarski's work. We've covered so much ground, from his groundbreaking contributions to our understanding of truth, to his nuanced account of logical consequence, to his profound insights into the nature of logical constants. It's really remarkable how he managed to weave together these seemingly disparate threads into a coherent and powerful vision of logic.
And what's particularly striking, especially for philosophers, is how he brought this mathematical rigor, this precision, to these traditionally philosophical problems. He forced us to really examine our assumptions and gave us new tools for analyzing these really fundamental concepts.
Absolutely. Tarski's influence on 20th century logic, mathematics, and philosophy, it's undeniable. He left us with a legacy of powerful concepts and rigorous frameworks that we're still grappling with today. And as we wrap up, I want to leave you, our listener, with a final thought. Given everything we've discussed, given Tarski's insights, especially this idea that the logical, non-logical distinction might be somewhat relative, could it be that our choice of logical framework, whether it's classical logic, intuitionistic logic, or something else entirely, could that actually shape the very kinds of philosophical truth that we can even express or discover? Or maybe, given the difficulty in pinpointing exactly what makes something a logical constant, how confident can we really be in the idea of a universally valid philosophical argument? These are just some of the questions that Tarski's work opens up, questions that we'll no doubt continue to grapple with for years to come.
Those are great questions. Really gets you thinking. And for our listeners who are ready to go even deeper, I highly recommend checking out the full Stanford Encyclopedia of Philosophy entry on Tarski. It's got lots of great detail and further reading suggestions. And of course, there's Tarski's own work, like his seminal piece, The Concept of Truth in Formalized Languages, and his papers on logical consequence. Those are really essential reading for anyone who's serious about these foundational issues in logic and philosophy.
Yes, absolutely. There's a whole world of fascinating and challenging ideas out there just waiting to be explored. So thank you for joining us on this deep dive. And until next time, keep questioning, keep exploring, and keep those philosophical gears turning.